Welcome to the deep dive. If you are, like us, intellectually curious about the hidden forces shaping our world, well, today we're getting into something really fundamental. The rotating magnetic field, the RMF. It's basically this invisible engine. You find it everywhere, powering so much of modern life. Think factory floors, even the fan in your room, perhaps. So let's try to unpack this. Simply put, the RMF is the magnetic field you get when you send carefully timed polyphase currents through coils arranged symmetrically.
Right, it's like creating the effect of a spinning magnet without actually spinning anything physically.
Exactly, a clever trick of physics.
And our goal today, our mission if you will, is to quickly trace the history and the core idea behind this, how we went from curious observations to, well, induction motors, huge generators, the works.
We want to connect those early sparks of insight to the massive power grids we rely on. But before we dive in, a quick thank you to our sponsor. This deep dive is brought to you by embersilk.com. If your intellectual curiosity extends to quality design, check them out at embersilk.com. Okay, let's rewind way back to the 1820s. We really have to start with Francois Arago, a French physicist.
1824.
He observed something odd, didn't he? These Arago's rotations had a copper disc spinning.
And a magnetic needle suspended above it started spinning too. He saw it happen, but the why was elusive. The mechanism wasn't clear at all.
Right. And then others jumped in.
Yes, English experimenters. Babbage, Herschel. They showed you could get the same effect by spinning a magnet under the disc. But it was Michael Faraday who really connected the dots.
Ah, Faraday, electromagnetic induction.
Exactly. He attributed the effect to induction, that crucial link between motion, magnetism, and electricity. Still, quite theoretical at this point.
But getting from that observation to something, useful, that was a big leap. Walter Bailey in 1879.
Yes. Bailey's primitive motor. It's almost painful to imagine.
He had to manually flip switches, right, to energize electromagnets one after the other.
Precisely. 4 of them, trying to force the magnetic field to rotate by hand. Essentially, it was, well, incredibly inefficient. Barely worked.
So that manual switching, that was the bottleneck.
Absolutely, which is why using alternating current, AC, to automatically create that rotating field was the game changer. And this is where the race really heats up.
Right, the parallel work. We have Galileo Ferraris in Italy.
Built a working AC model in 1885.
And Nikola Tesla, the Serbian-American inventor.
Developed his prototype around 1887, working independently, exploring the same fundamental idea.
And then, boom, 1888, Ferraris publishes his research.
And in the exact same year, Tesla gets his U.S. patent for the electromagnetic motor. Incredible timing.
Now, technically, you could use 2 phases, right? 2 currents 90 degrees apart.
You could, yes. A 2-phase system can produce an RMF. But almost everything today, globally, uses 3 phases. 3 sets of coils, driven by currents 120 degrees out of phase.
Okay, why 3? Why did that become the standard? It sounds maybe more complex.
It's actually about simplicity and stability in the long run. With 3 phases, 120 degrees apart, the resulting magnetic field vector, it rotates perfectly smoothly, and its strength, its magnitude, stays absolutely constant.
Ah, constant magnitude, like
Yep.
a perfectly balanced spinning top.
Exactly. A 2-phase system, to get rotation, often requires unequal currents or complex windings. That makes standardization, scaling up, conductor sizing, all much harder. 3-phase just worked better for building large, stable power systems. That symmetry was key.
That makes sense. Standardization is crucial for something like a power grid. Okay, so that RMF, created by the stationary part, a stator.
Yeah.
How does it make the motor actually turn, the rotor part?
Okay, so the RMF in the stator sweeps across the conductors in the rotor. The rotor is typically designed like a cage, short-circuited. This changing magnetic field induces currents within the rotor bar's eddy currents. Now you have currents flowing in the rotor, sitting inside the stator's rotating magnetic field.
And that creates a force.
Precisely. The Lorentz force, it pushes the rotor conductors, trying to make the rotor follow the rotating field. It's like the field is constantly dragging the rotor along with it.
Trying to make it catch up.
Exactly. But here's the crucial part, the sort of paradox of the induction motor. The rotor can never quite reach the same speed as the RMF.
It can't. Why not?
Think about it. If the rotor spun at the exact same synchronous speed, then from the rotor's perspective, the magnetic field wouldn't be changing anymore.
Ah, no relative motion between the field and the rotor bars.
Right. And if the field isn't changing relative to the rotor, there's no induced current. No induced current means no Lorentz force. The driving force disappears.
So it has to lag behind slightly.
Yes. That difference in speed, that lag, is called slip. It's absolutely necessary for the induction process to happen and for the motor to produce torque. The rotor is always chasing, never quite catching.
Fascinating. So, wrapping this up, we've gone from Arago seeing a needle twitch through Bailey's manual switching to this elegant three-phase RMF system.
A system that lets us efficiently generate, transmit, and use electrical power on a global scale, thanks to that inherent stability.
It really is fundamental.
It is. And maybe a final thought for you to consider. That constant magnitude of the three-phase RMF vector, that perfect rotational symmetry. It provided the stable physical foundation for electrifying the world. Imagine if it hadn't been so stable. How might even small imbalances or fluctuations at that fundamental level has completely altered the path or maybe even the feasibility of the large-scale power systems we now take for granted?